Good afternoon, everyone. My name is Ettore Zanetti, and I'm a postdoc at Lawrence Berkeley National Lab. And today I'm going to present you an MPC deployment work that we did in a commercial building in the lab. And my supervisor was David Blunt for the project, and the project was within the CalFlex sub-initiative, and Marianne is the PI. Diving right in, the building that we are considering, as I mentioned, is an office building at the lab. And we control 2 floors of the whole building, which is the office space, which is around 60,000 square feet. And the goal was, in this case, to optimize HVAC operation, not for energy consumption, but to reduce cost with dynamic prices while keeping comfort. The HVAC system of this building is, I would say, a bit peculiar. It's not your traditional VAV system. It's an underfloor air distribution system with reheats in the perimeter zones. And there are 4 rooftop units that, in particular on the right, you see a cross-section of the building and scheme of the HVAC. And the MPC controls the supply fan speed set point and supply air temperature set point, while for the perimeter zone on the heating side controls an offset on the thermostat to trigger a heating request for the thermal zone that's then carried out by the air source water heat pump. In terms of communication infrastructure, the core of the MPC is a server in one of our offices, and we collect weather forecast data from the National Oceanic Weather Service and the pricing information and some other boundary conditions from the CalFlex app from the project partners, while we get most of the building operational data from internal SkySpark database instance. And then the MPC does its optimization, and everything is stored, all the data and the optimization results is stored into a dedicated database, and the control inputs are sent to the building LC automation system through a SOAP interface. For the prices that I mentioned before, we wanted to test the different prices in different seasons, and in particular, the results I'm showing you today were not just the ones in the paper that we sent to the conference, but we carried out more studies throughout the year. And so we consider 4 seasons like summer, fall, winter, and spring. And the prices are highly dynamic and quite different between each other. In the summer, we have a single peak. In the spring, we have 2 peaks, for example. So the overall considered period for the results I'm going to show you in the next couple of slides is going to be basically from June 2023 to June 2024. And in the top chart, you have the daily energy consumption, while in the bottom is the external environmental conditions. Of course, I didn't highlight it, but the site, LBNL, is in Berkeley, so it's a relatively mild climate. There is definitely a seasonal component, but overall, in terms of temperature, at least, it's pretty mild throughout the year. And in gray, the gray areas are weekends where the system didn't work, so we didn't consider those, or periods where the data was a bit shaky, so we dropped it off. And in green instead, you have the 4 tests that we carried out with the 4 different prices. And those are 2 weeks of continuously running the MPC for each of the seasons, so summer, fall, winter, and spring. So what did we get from this testing? In this slide, there are a lot of plots, so I'm taking my time walking around it. Basically, here you have box plots highlighting a typical day, let's say, operation for the different seasons. So we group the data baseline and MPC by season. And on the right axis, you have the price for that specific season, while on the left axis, you have the HVAC consumption for the hour of the day for each of the days considered. And in general, for example, in winter, you can see that the MPC does a little bit of preheating, and it tries to avoid the main peak, which is in the afternoon. And in the summer, instead, it does a lot of pre-cooling at night. In Berkeley, the temperature outside is quite mild, so there is a lot of actually free cooling overnight to avoid the price peak. And in spring, instead, where we have 2 peaks, was interesting because sometimes the days were pretty warm, but because of the morning price peak, the MPC would prefer to not necessarily do a lot of pre-cooling at night, but instead focusing a lot of the consumption during the day. And fall is mixed. And this allowed us basically in terms of if you want to see a KPI, between the seasons, we were able to shift between 30 and 50% of the energy consumption within the 6 hours of the day where the price was the highest, with average power intensity shifted per square meter between 4 and 9. Of course, this should not come at the cost of comfort or like temperature differences between the baseline controller and the MPC at least. And in fact, here you have the same box plot, but in this case, instead of having the energy consumption, you have the temperature distribution for all the zones of the building for the different seasons. And you can see that more or less the trends are similar. Of course, the MPC shifting the demand tends to like pre-cool a little, preheat the building, and then tends to, let's say in the summer or in fall, it tends to let the building warm up a little more than the rule-based controller. But we think that in general, there were no complaints from the occupants of the building. And in this case, in this plot, you see a scatter plots with the discomfort. So the number of the daily uncomfortable degree hours for the MPC and for the rule-based controller. And there were no particular difference between the two. So what we wanted to do, as I mentioned at the beginning, was try to shift demand. And how does this translate then into cost savings? Here, I'm showing you the 4 charts with the baseline prices, which are the ones that we used to run the tests of the MPC. But we also wanted to see what's the benefit given just by the flexibility component versus just the benefit of like the fact that the MPC was running better with respect to the rule-based controller and saving energy in general. So what we did was considering the default price, which is highly dynamic. In the summer, you can have a peak of 8 cents, and basically in the early morning, energy is almost free. While in the red solid line, we called it a scaled, where we halved almost the ratio between the peak and the trough of the curve. And then there is also a cost and price line where basically the savings will be very similar to the actual energy savings. Of course, the MPC was optimized to run with the default line. So this is not necessarily a super fair comparison, but it gives a rough idea of what could happen. And here you see the scatter plots with those results, where on the x-axis you have the daily outdoor mean temperature, and on the y-axis for the first chart you have the energy consumption, while on the other chart you have the daily cost of running the MPC for the baseline controller in orange and in pink for the MPC, and it's also divided by season. I don't know how easy this is on the slides, so the different seasons, but in general, I would like you to focus on the fact that using the different prices for the energy consumption, the MPC did have savings with respect to the rule-based controller, especially more during the winter period. But once we start using dynamic prices, those savings drastically increase. And in fact, with the default scenario, with the very highly dynamic prices, we can save around 50% of the running cost of the HVAC, while with the, if you use the custom prices, that would be around 30%, which if you want to go on a yearly basis, it would be around $40,000 versus $20,000. So what did we learn from this experience? Well, first of all, this MPC experiment started from a previously run experiment by David Blum, where they were doing energy optimization, and since then, 2 years passed, and actually taking back that MPC and rerunning it took more effort than we thought, because the weather forecast service that we were using was not available anymore. The facility managers updated the ELC logic, and so we had to actually redesign the MPC around it. So really the practical issue of like coupling the MPC with the communication infrastructure of the building was the hardest part, because to be honest, changing from energy optimization to cost optimization was very, very easy and fairly seamless. And actually throughout all this experiment, we had to weight the parameters a little bit at the beginning, but then we didn't make any change to the code for all the testing, which I think is a nice testament to how flexible MPC is to respect, for example, to a traditional controller, where you'll have to like design a specific controller for each of those scenarios to achieve similar levels of flexibility. And all of this, of course, while keeping thermal comfort fairly similar to the the baseline controller. Another anecdotal example that happened was in the summer, there were some wildfires in Berkeley. And as I mentioned before, the MPC was trying to do a lot of free cooling and pre-cooling at night. But because of the smoke, facility operators actually shut off all the dampers. And so what the MPC was doing was recirculating the air inside the building and cooling it down with direct expansion coil. And I noticed this because like the one day from the other, the consumption basically tripled. And so I reached out to them, and they were like, yeah, we actually closed down all the air dampers. Ah, okay, good to know. But we had, there is actually an alarm system within the BMS, and basically I integrated this alarm system into the MPC itself so that it will automatically detect what I call like a smoke mode, so that in the constraints of the MPC, it will see that if it's a smoke mode, you should not take it into consideration the fact that you have a lot of like free cooling or you have outside air that you can use. So that's also something to consider. And lastly, throughout the whole implementation, something that was very important all the time was like having for a robust implementation, having like a robust system of alarms, emails, notifications. I'm sure all of the people that talked before me probably experienced it, but none of them talked about it. But that's to be honest, like of the code that runs the MPC, 90% of that code is that. 10% is the actual MPC algorithm. And so what do we see next? Well, first of all, we are going to publish the results that I just showed you because those are not public yet. And we also try to carry out a meta-analysis similarly to what Ashar did, but more focused on the cost of MPC, cost savings related to the flexibility component. And we see that in some studies, actually, the studies that are the highest cost savings is because there is this added value of flexibility that comes from free to MPC and can be a nice added value in general as an economic proposition. And we are also planning to lessen the burden of like the integration with the communication system by integrating semantics into our MPC algorithm for potentially automatic deployment in the future once BMS system will have a semantic layer. And lastly, we also plan to expand testing to different types of buildings because, of course, we know that our building is quite peculiar. And so it would be nice to have more tests in different buildings, more data points with long-term testings. That Ashar was saying it would be definitely very, very helpful. So thank you, everybody, for your attention. And I would like to thank also CalFlex Lab and UE for the funding and all the team that helped us carry out this project.
All right, fascinating talk. Thanks very much, Ettore. I guess I have a question again around sort of implementation costs. So it's challenging for researchers, actually, as Pradeep alluded to in the last talk. Often we have budgets and we have infinite cheap labor from grad students and things like that. So we may not think too hard about costs. Also, usually a research group that deploys in a building is doing it for the first time. Right? So you're training people as you go. And so it's not really a representative number of what the cost would be of the 100th or the 1,000th building if you were to scale it up in a startup, for example. Yeah. But you guys actually have a really cool case study because you've deployed in the same building with similar staff, right? But a second time. And then you sort of have to just resolve some previously solved problems. So I wonder, like, do you have a sense for how much do the deployment cost or effort reduce from that initial deployment to the second one?
I think it definitely drastically reduced because I took advantage of all, as I mentioned, like 90% of the code was the communication and really the data cleaning and the data processing, and that part was already there, and Dave did a great job at doing that. And so I greatly benefited from that. There was still some work to do, though, but I would say an order of magnitude less than what he did. So definitely that part could help if like scaling a general solution for sure.
So that could be a really interesting component of a future paper would be a cost benefit analysis, looking at your savings and then the deployment cost, but with that second deployment number in there, the order of magnitude less.
For sure. One idea for us now was to, in the paper I didn't show all the results, but was to get like, we don't know, to be honest, how much commercially a company will value, let's say, $20,000 or $40,000 per year. I don't know if that's enough to say we are going to have a free year payback time. So our idea is to like get out those numbers and see if then talk with folks in the industry and see if they say, yeah, that's a good number for us or not.
There was one in the chat. Do you want to read it? Yeah, so Harman Kai asked, on Minkai. On slide 7, there were several drop periods. Does that mean the controller was up and running about half the time?
No, so the drop periods are mostly weekends and holidays because the system goes on a schedule and the building is unoccupied and the HVAC is not working on the weekend. So we felt like those were not meaningful data. And then there is a bigger period, I would say, from in December, and that was a problem of the LC system where we didn't get any monitor data, so we didn't consider it.
Great, thank you.
Okay, thank you.
Right? Yeah, thank you.